So this is the last session of this conference, New Constructions 2. And this session has 2 talks. And the first one is Chosen Key Secure Even Mansell Cipher from a Single Permutation by Shan Fu, Chida, and Chunguo. And Shan Fu will give a talk.
Okay, thank you. Hello, everyone. My name is Shan Fu. Our topic is choosing key security even Mansell cipher from a single permutation. A fundamental cryptography problem is to construct a security block cipher from keyless permutations. A natural solution is the iterated even Mansell scheme. We call it IM for short. IM yields an n-bit block cipher by iterating XOR around K and some permutations. It abstracts substitution permutation network that has been used by several standards. Assuming the permutations are public and random, various of this scheme probably achieve various security notions, including indistinguishability, related key security, known key security, chosen key security in the sense of correlation, intractability, and indifferentiability. We focus on the indifferentiability of IM. Okay. In this setting, a distinguisher D is trying to distinguish the real world and the ideal world, which means a distinguisher is trying to distinguish the IM construction from a random permutation. In the real world, the distinguisher has oracle access to IM construction, and it also has oracle access to each internal permutations used in our construction. In the ideal world, the IM construction is replaced by an ideal block cipher, and to have the same interface in our construction, we need a simulator. The simulator has oracle access to ideal block cipher, and it must make up answers look consistent with random permutation. This property implies the IM cipher inherits all ideal cipher properties defined by single-stage security games, including security against related key and chosen key attacks. Okay. Block cipher indifferentiability analyses are typically lengthy and require unnecessary constructions. And their influences are not as notable as when applied to hash function. To remedy weak definitions have been proposed. In particular, to formalize chosen key security. The previous work used the notion of correlation intractability. Means that no chosen key adversary can find the input output of the block cipher satisfies immiscible relations. This notion is again only achievable by ideal model beside the block cipher. To establish CI in the ideal model, we consider the distinguisher is sequential. It is called sequential indifferentiability. Okay, and it restricts the pre-order of distinguisher to be primitive constructing sequential. In the first step, a distinguisher creates internal permutations and the simulator. The green arrow shows this step. In the second step, it creates the IM construction and the ideal block cipher E. In this situation, the distinguisher could not do any more queries with 3 arrows because we restrict the pre-order of distinguisher to be primitive construction sequential. Of course, it is weak than field indifferentiability. The sequential indifferentiability notion has the advantage of being simpler and easier to use in the proofs, but it is still strong to imply correlation intractability. Okay. Besides initial positive result on the general IM model, another attractive line of work has been set to seek for minimizing IM cipher for certain security properties. In the previous work, the single key UML variant EMIP without any non-trivial key schedule was called sequential indifferentiability at 4 rounds. A natural next step is to investigate whether sequential indifferentiability is achievable using a single permutation. Unfortunately, in another of our work, even in the weak model of sequential indifferentiability, the single key, single permutation UML variant EMSP remains insecure, regardless of the number of rounds. Concurrently, we found an attack that make just one permutation query and one interpreting query. Intel, first, the distinguishing queries px to get y, and let k be equal to x XOR y. So u is equal to y and v is equal to x. So in the EMSP construction, a single input-output pair of the permutation already yields a 50-round EMSP. Given our negative results, to achieve security, one must enhance 4-round EMSP by using an orphan key schedule. Okay, in this work, the orphan permutation phi can be a linear osmosis or cyclic shift. We call this EMSP variant EMSP phi. Next is our main work. We propose the EMSP phi with a single permutation achieves the notion of sequential indifferentiability. And it is the minimal IM solution scheme. In general, to establish indifferentiability type security, the first step is to construct a simulator that resists a barriers attack. Then it remains to argue that the simulator is inferential and the simulator gives rise to an ideal world that is indistinguishable from the real world. So the question is, how do we build a simulator? We use the chain complete technique. It requires the simulator to detect partial chains formed by the queries of the distinguisher and complete chains in advance. To simulate answers that are consistent with random permutation, the simulator must use the answers from permutation to define some simulated answers. This action is called adaptation. Then the core idea of our simulator is internal values are secret and random. Okay, as shown in this picture, it is a switching that the simulator must detect. When decreases px, the simulator first checks whether it can form a switching. In this switching, the first 2 rounds are records already stored in the simulator's table, and this is the query can be linked exactly at the 3rd round on the right. If a switching is formed, then the simulator completes a function of EMSP phi in advance. Firstly, the simulator computes the required round k decided on the switching, and x4 can be obtained. Then by querying ideal block cipher and simple commutation to obtain y4, so we can get a function of EMSP phi where x4 y4 is called the adaptation record. Okay. When decrease p in the opposite direction, the simulator also needs to check whether the switching is formed. In this switching, the last rounds are records already stored in the simulator's table, and latest query can be linked exactly at the 1st round on the left. If a switching is formed, then the simulator also needs to complete a function in advance. Okay, it is like the previous switching case, but in the opposite direction. Firstly, the simulator computes the required round k decided on the switching, and then by querying ideal block cipher and simple commutation to obtain x1, y1. So we can get a function of EMSP phi, where x1, y1 is an adaptation record. After completing the switching check, the simulator also needs to check the 2 chain. When decrease px, the simulator checks the 2 chain in this picture. In this 2 chain, the first round is a record already stored in the simulator's table, and of course, the latest query can form a 2 chain with all previous records. In this case, the latest query is to the right of the previous record. If a toolchain is formed, then the simulator completes a portion of EMSP5 in advance. Okay. Firstly, the simulator computes the required round key decided on the toolchain. Secondly, the simulator internally query P to obtain X4, Y4. These values are secret and won't handled immediately. So this internal query won't trigger a new simulator circle. Then by querying ideal block cipher and simple computation to obtain X1, Y1, so we can get a function of EMSP5 where X1, Y1 is an adaptation record. Similarly, when D queries P in the opposite direction, the simulator also needs to check whether the toolchain is formed. In this toolchain, the last round is a record already stored in the simulator's table, and the latest query is to the left of the previous record. Okay, it is like the previous toolchain case, but in the opposite direction. The simulator internally query P to obtain X1, Y1, and X4, Y4 is an adaptation record. Okay. After introducing the simulator, we simplify the previous model. E is an ideal block cipher, S is the simulator, and P is the permutation with n bit. So the question is how to get distance between ideal world and the real world. It remains to establish two claims for any distinguisher D. Firstly, the simulator has abundant complexity. Secondly, the ideal world and the real world are indistinguishable. To this end, we use an intermediate system. In this system, the simulator has Oracle access to E and P. A distinguisher queries the simulator and the EMSP5 with Oracle access to the simulator. So getting distance between ideal world and the real world can be two steps. We first consider the distance between ideal world and the intermediate system. We can see that a distinguisher first queries the simulator with Oracle access to P and E. If the pair EP is good, the answers distinguisher result are identical both in ideal world and the intermediate system. On the left side, E is an ideal block cipher and the EMSP5 is a real structure. So the distance between ideal world and the intermediate system depends on the permutation P. Next, we consider the distance between intermediate system and the real world. Notice that real world only has access to the permutation P, so the situation is different. The most important thing is how to change the pair EP to P. So we use the randomness mapping to solve it. Firstly, we define a map lambda. The map lambda is defined for any pairs EP as follows. Okay, run D and consider the table of the simulator at the end of the execution. Then fill all undefined entries in the table with special symbol. If the pair EP is good, the simulator never overrides an entry in the table. In other words, partial permutation pi is good if it has a good preimage by lambda. Secondly, we see that permutation P contains a partial permutation pi if the occurring on all entries. Okay, by definition of the randomness mapping, if the partial permutation pi is good, the outputs of intermediate system and the real world are equal for any pair EP. So we can use the partial permutation to find out the distance between intermediate system and the real world, thereby find out the distance between ideal world and the real world. So we finish the proof of the sequential indifferentiability of EMSP5 with a single permutation. The previous research stopped at using independent permutations, but there is a gap between such result and popular standards. This work may bridge this gap. Also, it is the first indifferentiability type security for block ciphers using identical round functions. Finally, we have a summary of our work and previous works. It shows that the number of primitives, case scheme, simulator complexity, and the security bound of our work and the previous works. Thank you for listening. And any question?
Thank you for a nice talk. So are there any questions in Beijing? No questions in Beijing?
There is a question in Beijing.
Thanks for your interesting talking. I have one question. You discussed 4 rounds of IAM, which uses a single permutation. Have you ever considered reducing the number of rounds, say 3 rounds of IAM? Thank you.
You mean 3 round IAM?
Yeah.
Okay. Okay, in this table, the previous work holds EMKD is sequential indifferentiability, but their case scheme is random oracle. Okay, so we actually consider 3 round IAM at first, but found some negative results. We found an attack that can be applied to 3 round IAM without any non-trivial case schedule, and this result is shown in our paper. Okay.
Okay. Did you design a block cipher based on your results of your work?
Applications?
Did you design?
No. This work is mainly focused on the proof of IAM security. Real world applications are future work.
Okay, thank you.
Okay, thank you.
Are there any other questions in Beijing?
Yeah.
So you have any questions?
Thanks for your presentation. I have a question. Whether sequential indifferentiability imply correlation interability?
Correlation intractability, you mean? Oh, okay. Okay. Correlation intractability shows that block cipher has a negligible probability of finding some universal relations both in the real and ideal worlds. This is consistent with sequential indifferentiability. The sequential distinguisher can't distinguish the real world from the ideal world. Okay.
Okay, yes, thank you.
You're welcome.
So are there any questions from Kobe or online or Beijing Ajin?
Oh, there is another question in Beijing.
I was wondering that if you're familiar with the minimizing the 2-round tweakable information was published in the Asian Crypto 2020, and he said they analyzed the 2 tweakable information ciphers with 1 permutation, but they uses 2 hash functions and with only 1 permutation. I think your works are kind of familiar. So have you ever done anything like that? For example, the 2 rounds with 1 permutation and with 2 hash function. I think that could be kind of, yeah. Have you ever considered that?
Hash function?
Yes, the work in the Asian Crypto 2020, and he have done an analysis, the security analysis in 2 round tweakable information. and they are also use one permutation. Can you compare your work with them?
There is no such work for two-round even Mansell.
It's not Ivermanson, but it's tweakable Ivermanson. It's kind of, yeah,
No.
tweakable Ivermanson is kind of.
This work not considered in this case.
Okay, thank you.
Yes, you are welcome.
So there may be other questions, but I think now is the time for the next talk. So anyways, I'd like to thank Xiangje Fu, Lin. Thank you. And so the next talk, the last talk of this conference, is from Kobe. The title of the talk is Generalized Feistel Structures Based on Tweakable Block Ciphers by Kazuki Nakaya and Tetsu Iwata. And Kazuki Nakaya will give a talk.
Thank you. Thank you for the introduction. My name is Kazuki Nakaya. I will present generalized Feistel structures based on tweakable block ciphers. This is a joint work with Tetsu Iwata. First, I will talk about introduction. Block cipher is a key permutation and mapping from a key space and an n-bit space into an n-bit space. If we fix the key, EK is a permutation over n bits. N is called a block length. We will write NBC for this block cipher. Construction of a secure block cipher is one of the most important problems in symmetric key cryptography. We consider the security of a block cipher E as pseudorandom permutation and a strong PRP. A PRP adversary is given oracle access to an encryption oracle EK in the real world, and it is given oracle access to random permutation pi in the ideal world. The goal of adversary is to distinguish the two cases, and we measure the success probability with this advantage function. An SPRP adversary is given oracle access to an encryption oracle and a decryption oracle of EK in the real world, and it is given oracle access to pi and inverse function in the ideal world. Ruby and Rockfox shows that the random Feistel cipher with n-bit pseudorandom functions is a PRP, and for random Feistel with n-bit PRFs is an SPRP. There are various approaches for designing a secure block cipher. Generalized Feistel structure is one of the ways to construct a block cipher. There are various types of JFS, including unbalanced JFS, type 1, type 2, and type 3 JFS. The probable security of type 1, type 2, and type 3 JFS was presented by Chen et al. 2D-1 round type 1 JFS is a PRP. D+1 round type 2 JFS is a PRP, and D+2 round is an SPRP. D+1 round type 3 JFS is a PRP. This construction uses PRFs as primitives. A tweakable block cipher generalizes a block cipher to take an additional input called a tweak. A TBC is a mapping from a key space, a T-bit space, and an n-bit space into an n-bit space. If we pick the key and tweak, the EKT is a permutation over n bits. We will write TN-TBC, for a TB tweak, and N-bit block TBC. Initially, TBCs has been constructed from block ciphers. The other direction to construct a block cipher from TBCs was initiated by Minematsu. Koro et al. Instantiated a Feistel structure with NLTBC to obtain 2NBC. Minematsu and Nakamichi et al. Analyzed the TBC-based counterparts of the unbalanced JFS. This construction uses TBCs with D-1 times N bit tweak and N bit block. The figure on the right shows this DNBC. Type 1 and Type 2 and Type 3 JFS based on TBCs can naturally be defined. We change N-bit PRF and XOR in PRF-based JFS into NLTBC to construct TBC-based JFS. And the probability of this structure is open. Our purpose of this work to formalize the structure and consider the probability of these counterparts. Next, I will show our contributions. This table shows our results in the security proof. In the table, here is the number of queries. We use NLTBCs to obtain DNBCs. And we identified the number of rounds needed to achieve birthday band security and BBB security with respect to N. For TBC-based type 1 JFS, we prove PRP security and SPRP security separately because this construction has different security characteristics depending on the direction of the operation. For TBC-based type 2 and type 3 JFS, we prove SPRP security. We also analyze the optimality of our results with respect to the number of rounds and the attack complexity. We note that the constructions we consider in this paper have iterative structures. This table is a summary of previous results. In the results showed by Shen et al., it is a parameter that specifies the number of rounds. Shen et al. Proved stronger security bands than previous results by increasing the number of rounds. Next, I will explain our security proof. In our security proof, we use coefficient H technique. We write this probability for interpolation probability in the real world and in the ideal world. A transcript set that satisfies these inequalities is called an attainable transcript. In coefficient H technique, we partition all the attainable transcripts into good ones and bad ones. Assume that there exist epsilon such that for all good transcripts, the ratio of the interpolation probabilities is larger than or equal to 1 minus epsilon. Then the upper bound, the advantage is the sum of epsilon and the probability to have bad transcripts in the ideal world. Epsilon and the probability to have bad transcripts depend on the definitions of oracles and bad transcripts. The definitions of real-world oracle R is TBC-based JFS. For each query, an adversary makes are records of the internal states in S. The adversary A gets all the internal states S after A makes all the queries. For example, this figure shows type 1 GFS with D is 4 and R is 6. This oracle computes the internal states S1 and S2 with P1 and P2, and computes the ciphertext with P3 to P6. The definitions of the ideal world oracle I is DN bit random permutation pi. For each query, I use this dummy TBCs to compute dummy internal states. The dummy internal states have the same probability distribution as in the real world. The adversary A gets all the internal states S after A makes all the queries. For example, this figure shows the ideal world oracle I with D is 4 and R is 6. This oracle computes the internal states S1 and S2 with P1 and P2, and computes the ciphertext with pi. To define the set of BAT transcripts, we consider the conditions that can only hold in the ideal world. In the real world, for TBCP, let xi, pi, and yi be the input, tweak, and output for the ith query. If ti xi is equal to tj yj, then we must have yi is equal to yj. Similarly, we have ti yi is equal to tj yj, then xi is equal to xj. There are conditions that can only hold in the ideal world because we may not have these equalities. These conditions can hold at TBCs that are not used in the ideal world. A transcript set is a BAT transcript if at least one of these conditions is satisfied. For example, in the case of type 1 GFS with D is 4 and R is 6, 2n-bit BAT collisions can occur at P3 to P6 that are not used in the ideal world. As you can see in the figure, the BAT collisions at P3 are the collision at S2, M4, and S2, C2. For the other TBCs, there are two BAT collisions. We compute the probability to have BAT transcripts in the ideal world by taking summation of relevant BAT probabilities. For R is 2D minus 2, we compute this upper bound. Next, I will show the matching attack. For example, this figure shows chosen plaintext attack against type 1 GFS with D is 4. In the figure, we fix M1, M2, and M3, and red, dashed, and black lines denote a zero difference, a non-zero difference, and a random difference. We prove busted bound security with R is 6 and BBB security with R is 10 for this construction. In the case R is less than 6, in the real world, a zero difference always exists in a ciphertext block. Therefore, this construction is distinguishable with two queries, implying that 2D minus 2 is the optimal number of runs for busted bound security. In the case R is larger than or equal to 6 and less than 10. In the real world, the collision probability at ciphertext block, C2 in the figure, is about 3 times larger than in the ideal world. If S4 or S5 or C2 randomly collide, then we have collision at C2. Therefore, this construction is distinguishable with 2 to the n half queries, implying that 3D minus 2 is the optimal number of runs for BBB security. Finally, I conclude this talk. We formalize TBC-based type 1, type 2, and type 3 GFS and presented their probable security. In the security proof, we identified the number of runs to achieve birthday bound security and BBB security. We also presented attack to show the optimality of our results with respect to the number of runs and attack complexity. As open questions, we do not know if an attack with 2 to the n complexity exists when the number of runs is larger than or equal to that for BBB security. Also, we leave the analysis to obtain stronger security bounds by increasing the number of runs. This paper focuses on distinguishability notion. Indifferentiability of TBC-based GFS is open. Here are the references. I'd like to close our presentation. Thank you for listening.
Thank you for the nice talk. So do we have any questions from Kobe? Questions or comments? So far, no question from Kobe. And how about Beijing or online? Are there any questions?
No questions.
Okay, thank you. Then I have one question. So you say that we do not know if an attack with 2 to the power n complexity exists for BBB secure construction.
Yes.
So my question is, did you find any kind of attack of complexity 2 to the power 2n or 2 to the power 3n? Something?
No.
No? No attack. Or are there any kind of trivial bound for attack complexity?
So, could you repeat the question?
Are there any kind of trivial upper bound for attack complexity to break the BBB secure construction?
No attack breaks the BBB security.
Okay, so probably anyways, you didn't find any attack to break the construction.
Yes, yes.
Okay, thank you. So are there any additional questions or comments from Beijing or online? No? So if there is no more questions, then I'd like to thank the speakers of this session and the speakers of this conference, all the speakers of this conference again. Thank you.